The sun releases more energy in 1 second than humanity has consumed in its entire history. Not just modern history. All of it. Every fire ever lit. Every engine ever turned. Every light ever switched on. 1 second of the sun outweighs all of that. And yet, of all that power streaming outward in every direction, Earth catches less than a billionth of it. A tiny sliver. A fraction so small it barely registers. The rest just flies past us. Lost to the void. We live on scraps. If you enjoy these deep dives, you can subscribe. It helps more than you think. There's something uncomfortable about that realization. We talk about energy crises, about running out of oil or coal, about the limits of solar panels and wind turbines. But the actual problem isn't scarcity, it's reach. The sun isn't holding back. It's pouring out more energy than we could ever need. We just haven't figured out how to catch it. Not really, not in any meaningful way. And that gap between what's available and what we can actually use defines almost everything about our species, our technology, our economy, our future. All of it hinges on energy. And right now, we're standing in the middle of an ocean, dying of thirst. In 1960, a physicist named Freeman Dyson wrote a paper that changed the way people thought about advanced civilizations. It wasn't a long paper, just 2 pages, but the idea inside it was enormous. Dyson wasn't interested in what humanity could do tomorrow or next year. He was thinking in geological time, in civilizational time. He was asking what a species might look like after thousands or millions of years of technological growth. And he realized something simple. Energy is the bottleneck, always. No matter how advanced you get, no matter what you invent, you can't escape thermodynamics. You need power, and if you want to keep growing, you need more of it. Eventually, planetary resources aren't enough. Wind and geothermal and fossil fuels, and even ground-based solar, all of it plateaus. You hit a ceiling, and if you want to go further, you have to look up. Dyson suggested that a truly advanced civilization wouldn't just harvest a fraction of its star's energy. It would capture all of it, or as much as physically possible. He imagined a structure, or a system, that surrounded the star entirely. A shell, a swarm, something vast enough to intercept the light before it escaped into space. He called it a megastructure. Other people started calling it a Dyson Sphere. The name stuck, but the idea got misunderstood almost immediately. When most people hear Dyson Sphere, they picture a solid shell, a rigid structure wrapped around the sun like a Christmas ornament, something you could walk on, something with an inner surface facing the star, bathed in perpetual daylight, and an outer surface facing the cold. It sounds like science fiction, and it is, because a solid sphere around the sun is impossible. Not difficult, not impractical, impossible. The physics don't work. There's no material strong enough to hold its shape under those conditions. Gravity would pull it apart. The sun's radiation would cook it. The sheer scale would crush any attempt at structural integrity. A rigid shell around a star is a fantasy. But Dyson never suggested a solid shell. That was a mistake people made later. What he actually described was something more elegant. A swarm. Millions, maybe billions, of independent objects orbiting the star in a loose cloud. Each one a solar collector. Each one harvesting light and converting it into usable energy. They wouldn't touch each other. They wouldn't form a single structure. They'd just float there, orbiting, drinking in sunlight, beaming power back to wherever it was needed. And together, over time, they'd intercept more and more of the star's output. Not all of it, probably, but enough. Enough to make the civilization using them unrecognizable by today's standards. That version is possible. Difficult, yes. Absurdly difficult, but not physically impossible. And that distinction matters, because when we talk about how close we are to building a Dyson Sphere, we're not talking about magic. We're talking about engineering. Hard, patient, multi-generational engineering. The kind that doesn't care about quarterly earnings or election cycles. The kind that unfolds over centuries. Before we get into the how, we need to understand the why. And that starts with a scale. In 1964, a Soviet astronomer named Nikolai Kardashev proposed a way to classify civilizations based on their energy usage. It's called the Kardashev scale. It's simple, maybe too simple, but it's useful. Type Y civilizations can harness all the energy available on their home planet, every bit of sunlight that hits the surface, every geothermal vent, every ocean current, everything. Type 302 civilizations go further. They harvest the energy of their entire star, not just what lands on their planet, all of it. Type 3 civilizations control the energy of an entire galaxy. We don't need to think about Type 3. It's so far beyond us, it might as well be magic. Humanity isn't Type 1, not even close. We're somewhere around 0.7 on the scale. We use a fraction of Earth's available energy. Most of our power still comes from burning ancient organic matter we dug out of the ground. We've gotten better at harnessing wind and sunlight, but we're nowhere near capturing everything the planet offers. And the gap between where we are and Type 1 is already enormous. The gap between Type 1 and Type 2 is unimaginable. It's not a step up, it's a leap across an abyss. A Type 2 civilization doesn't just have more energy. It has so much energy that scarcity stops being a concept. You don't ration power. You don't worry about efficiency the way we do. You have enough energy to disassemble planets for raw materials, enough to run continent-sized computers, enough to push spacecraft to a significant fraction of light speed, enough to terraform worlds, enough to do things we don't even have words for yet. And all of it starts with the star. So the question isn't really whether we should build a Dyson Sphere. The question is whether we can, and if so, how long it would take. Let's start with what we'd actually build. A Dyson Swarm isn't a single object. It's a population. Each collector is its own satellite. It orbits the sun independently, following its own path, obeying the same orbital mechanics that govern planets and moons. These collectors are probably thin, light, maybe just a few atoms thick in places. They need to be, because launching mass into space is expensive. Every kilogram costs energy and resources. So you optimize. You make them as efficient as possible. They absorb sunlight on one side, convert it to electricity or microwaves or lasers, and beam that energy back to wherever it's needed. Earth, maybe, or a space station, or an asteroid mining outpost. The power doesn't have to travel through wires. It moves through space as directed radiation. Each collector is small compared to the sun, but there are a lot of them, and that's the point. You don't build one massive panel. You build thousands, then millions, then billions. Each one adds a little more to the total. Over time, they start to form a cloud around the star, not a solid surface, a haze, a fog of orbiting machines, each one sipping energy from the light that would otherwise vanish into the dark. The more collectors you add, the more of the sun's light you capture. At first, it's negligible. A few collectors don't make a dent, but the growth is exponential. If you can build one collector, you can build two. If you can build 1,000, you can build 10,000. Eventually, you're not limited by labor or time. You're limited by raw materials. And there are a lot of raw materials in a solar system. The engineering problems are staggering. First, materials. You need an enormous amount of them, more than Earth can provide. Strip mining an entire planet for metals and silicon isn't practical. It would destroy the biosphere, and even then, it wouldn't be enough. You'd run out long before you had a meaningful percentage of the sun covered, so you look elsewhere. The asteroid belt is the obvious choice. Millions of rocks, rich in metals, with no ecosystems to worry about. You send machines to mine them, refine the ore in space, turn it into solar collectors right there, in orbit, without ever bringing it down to a planet. Mercury is another option. It's close to the sun, which means less travel time for materials. It's also a dead world. No atmosphere, no life, no reason to preserve it. You could dismantle Mercury piece by piece over thousands of years, feeding its mass into the construction process. Some proposals suggest using the planet's material to build the first wave of collectors, which then provide the energy to mine more material faster. A bootstrapping process. Slow at first, then faster, then exponentially faster. But mining is just the start. You need to refine the material, smelt it, shape it, assemble it into functional collectors. And you need to do all of this in space, because launching finished products from a planet's surface is prohibitively expensive. Earth's gravity well is deep. It costs a fortune in fuel to lift anything out of it. So you don't. You build the infrastructure in orbit. You create factories that float in the void, powered by the sun, fed by asteroid ore, staffed by robots. No humans required, at least not many. Self-replicating machines are key. You can't send enough people or equipment from Earth to build billions of solar collectors. It's not feasible. But you could send a small number of machines capable of building copies of themselves. They land on an asteroid, mine the material, refine it, and construct more machines. Then those machines do the same, and so on. The population grows. The construction rate accelerates. It's the only way the math works. Without self-replication, you're stuck with linear growth. With it, you get exponential growth. And exponential growth is the only thing that makes a Dyson Swarm possible within any reasonable time frame. Of course, self-replicating machines come with their own problems. They need to be reliable, autonomous, smart enough to adapt to unexpected conditions, but not so complex that they break down constantly. They need power, which means you need solar panels to power the machines building the solar panels. They need to avoid making mistakes, because a single flaw in the replication process could propagate through millions of copies, and they need to be controlled, somehow, so they don't just keep replicating forever, consuming everything in the solar system. The idea sounds almost biological, and in a way, it is. You're creating an artificial ecosystem, one that feeds on metal and sunlight and grows until you tell it to stop. Then there's the question of stability. Millions of objects orbiting the sun means millions of potential collisions. Space is big, and the odds of any two collectors hitting each other are low, but low odds over a large enough population means it will happen regularly. You need collision avoidance systems, navigation, communication between collectors so they can adjust their orbits dynamically. You need repair drones, salvage operations for damaged units, a logistics network that spans the inner solar system. It's not a static structure. It's alive, in a sense, constantly shifting, constantly being maintained. Heat is another issue. Solar collectors absorb light, but they also radiate heat. That's unavoidable. Thermodynamics won't let you convert energy with perfect efficiency. Some of it becomes waste heat, and that heat has to go somewhere. In space, the only way to get rid of heat is radiation. So every collector glows faintly in the infrared. That's actually one way astronomers think they might detect alien Dyson spheres, if they exist, by looking for stars that seem dimmer in visible light, but brighter in infrared. A star wrapped in a cloud of collectors would look odd, cooler than it should be in some wavelengths, warmer in others. It would stand out. For our own Dyson Swarm, waste heat isn't just a detection problem, it's an operational one. If collectors get too hot, they stop working efficiently. So you need cooling systems, radiators, heat sinks, and you need to position the collectors carefully so they don't heat each other up. Orbital mechanics becomes a delicate balance between maximizing energy capture and managing heat. Power transmission is the next challenge. You've built the collectors. They're absorbing sunlight. Now what? How do you get that energy back to Earth, or to wherever it's needed? You can't run a cable. Space is too big, and a physical connection would be a nightmare to maintain. So you beam it. Microwaves, probably. Or lasers. You aim a focused beam of energy at a receiving station, and that station converts it back into electricity. It works. We've tested the concept on small scales, but doing it across millions of kilometers, with billions of collectors, all sending power to different locations, is a logistics problem that makes modern power grids look trivial. And all of this assumes nothing goes wrong. But things will go wrong. Collectors will fail. Asteroids will drift into the swarm. Solar flares will fry electronics. Micrometeorites will punch holes in delicate panels. Equipment will wear out. Software will glitch. You need constant maintenance, constant monitoring, an entire support infrastructure just to keep the system running. And that infrastructure has to be built and maintained too. It's overwhelming. And we haven't even talked about cost. Building a Dyson Swarm isn't something you fund with a national budget. It's not a 10-year project or a 50-year project. It's a species-level project, multi-generational. The people who start it won't live to see it finished. Neither will their children or their grandchildren. You're talking about centuries of sustained effort, at minimum, probably longer, and that raises questions that go beyond engineering. Political questions, social questions. How do you get humanity to agree on something like this? How do you maintain focus across generations? How do you prevent conflicts over resources, or sabotage, or simple apathy? There's no historical precedent for a project this large. The pyramids took decades. Cathedrals took centuries, but they were local. They involved thousands of people, not billions. And they didn't require inventing entirely new technologies just to get started. A Dyson Swarm does. We'd need to master asteroid mining, autonomous robotics, space-based manufacturing, and energy transmission on a scale we've never attempted. We'd need to industrialize the moon, probably. Use it as a base for launching materials and equipment into deeper space. We'd need to build shipyards in orbit, fuel depots, repair stations, an entire off-world economy, independent of Earth. None of this is impossible, but none of it is close. Right now, humanity uses about 580 million terajoules of energy per year. That sounds like a lot. It is a lot compared to what we used a century ago, but it's nothing compared to what the sun puts out. The sun releases about 400 trillion joules every second. We're not even rounding errors. We're invisible, and we're still struggling to move away from fossil fuels. We're still debating whether to build more solar panels on Earth, let alone in space. We've put solar panels on satellites. The International Space Station runs on solar power, but those panels are tiny. A few square meters. A Dyson Swarm would require billions of square kilometers. We've never built anything on that scale. We've never even tried. The largest structures we've put in space are a few hundred meters across. A single Dyson collector might be kilometers wide, and we'd need billions of them. We're not ready. Not technologically, not economically, not politically. We're barely ready to think about it, but that doesn't mean we'll never be ready. The path from here to a Dyson Swarm is long, but it's not invisible. We can sketch it out. We can see the steps, even if we can't take them yet. It starts small, smaller than most people imagine. You don't begin by launching solar collectors toward the sun. You begin by learning to live off-world, permanently. Not just a space station with rotating crews, but actual infrastructure. A moon base, maybe. A mining outpost on an asteroid. Places where people, or more likely robots, can work for years at a time without resupply from Earth. The moon is a logical first step. It's close, 3 days away. It has resources, ice at the poles, metals in the regolith. You could build a small industrial base there. A refinery, a launch facility. Use lunar material to manufacture equipment, then launch it into space using the moon's shallow gravity well. It's easier to lift mass off the moon than off Earth. Much easier. You save fuel, you save money, you build momentum. From the moon, you reach out. Asteroids, near-Earth objects first, then deeper into the belt. You send mining drones. They attach to rocks, drill into them, extract metals, and either bring the material back or process it on site. Slowly, you build up a stockpile. Iron, nickel, platinum, rare earths, everything you need for advanced manufacturing. And you do it in space, where gravity isn't fighting you. At some point, you construct the first space-based factory. It doesn't make solar collectors yet. It makes tools, parts, components. It's small, experimental, but it works. And once you have one, you can build another, then 10, then 100. Each factory makes it easier to build the next one. The process feeds itself. Eventually, you're ready to build the first collector. It's crude, inefficient, smaller than you'd like, but it works. It orbits the sun, absorbs light, and beams energy back to a receiver in Earth orbit. The amount of power is negligible, a rounding error, but it's proof of concept. You built something. You made it work, and now you can build more. The second collector is easier than the first. The 10th is easier than the second. By the time you've built 1,000, the process is almost routine, and if you've managed to create self-replicating machines by then, the growth becomes exponential. Each collector provides energy to build more collectors. Each factory builds more factories. The numbers start to climb. 1,000 becomes 10,000. 10,000 becomes 1,000,000. And the sun starts to dim, not to the naked eye, not yet, But if you measured it carefully, you'd see the output dropping, a fraction of a percent at first, then more. This process takes centuries, maybe a millennium. There's no shortcut. You can't brute force it with money or willpower. You're constrained by physics. By the time it takes to mine an asteroid, refine the ore, build a collector, and launch it into the right orbit. Even with automation, even with perfect efficiency, it's slow, but it's steady. And steady is enough if you don't give up. By the time you have 1 billion collectors, the sun looks different, not darker exactly, but softer. The light that reaches Earth is filtered, dimmed by the swarm. The climate changes, not catastrophically, not yet, but it's noticeable. You have to adjust. Maybe you remove some collectors from the orbits that block Earth's sunlight. Maybe you accept the change and adapt. Either way, you're no longer a planetary species. You're a solar species. You live in the orbits around your star, not just on the surface of one world. At some point, Earth becomes less important, not irrelevant, but less central. Most of your energy comes from the swarm now, not from ground-based sources. Most of your industry is in space. Most of your resources come from asteroids and disassembled planets. Earth is where humanity started, but it's not where humanity lives anymore. Not entirely. The swarm is home now. The sun is home, and you're still growing. How long until the swarm is complete? That depends on what you mean by complete. You'll never capture 100% of the sun's energy. That's impossible. Some light will always escape, but you could get close. 90%, 95%, and at that point, you've done it. You're Type 2. You've harnessed your star, and everything changes. Energy becomes nearly limitless. Not infinite. Nothing's infinite, but so abundant that scarcity, as we understand it, vanishes. You don't ration power anymore. You don't build smaller to save energy. You build as large as you want. You run calculations that would take modern supercomputers millennia. You power cities in space, hanging in orbit, lit by transmitted energy from the swarm. You terraform planets. Mars gets a thicker atmosphere, warmer temperatures. Venus gets cooled. Its toxic air stripped away. It takes energy, enormous amounts of it, but you have it now. You have more than you need. Transportation changes. You're not limited by fuel anymore. You can accelerate spacecraft to a significant fraction of light speed, given enough time and energy. The outer solar system, once impossibly remote, becomes accessible. Pluto, the Kuiper Belt, the Oort cloud. You send probes, maybe even ships with people on them, if people still exist in a form we'd recognize. And beyond that, other stars. Still far, still difficult, but no longer impossible. With enough energy, you can think about interstellar travel. Slow travel, maybe. Generation ships. Or something faster, if you figure out how. The energy is there. The rest is just engineering. Science explodes. Experiments that were too expensive or power-hungry become routine. Particle accelerators the size of planets. Simulations that model entire galaxies. Quantum computers the size of moons. You answer questions that seemed unanswerable. You probe the deepest mysteries of physics because you have the tools now, the energy to run them, the infrastructure to build them, and the time, because you're not worried about survival anymore. You're past that. You're exploring. Culture shifts. It has to. A civilization with that much energy doesn't look like ours. It doesn't have the same constraints, doesn't have the same conflicts. Wars over resources become pointless. There are no scarce resources, not in any meaningful sense. You can make anything you need, given enough time and material. And material is everywhere. You're surrounded by it. Asteroids, dead moons, gas giants, all of it raw material waiting to be used. Population grows, or maybe it doesn't. Maybe people decide they don't need to grow anymore. Maybe they spread out instead, each person or group claiming a small piece of the solar system, a habitat in orbit, a moon, an asteroid. Privacy becomes easy when you have that much space. Solitude, if you want it, or community if you prefer. You build what you want, live how you want. The energy supports it all, but there are costs. There always are. Even a Dyson Swarm, even with all that power, can't escape thermodynamics. You're still generating waste heat, enormous amounts of it. The solar system gets warmer, not immediately, not catastrophically, But over time, the heat builds up. You have to manage it, radiate it away. Maybe you build massive radiators, structures designed purely to dump heat into space. Maybe you accept that the inner solar system gets hotter and move your habitats outward, where it's cooler. Either way, you're reshaping your environment, not just the planets, the entire system. And you're visible, very visible. A Dyson Swarm glows in the infrared. Any alien civilization with decent telescopes could spot it from light years away. They'd see a star that looks wrong, too dim in visible light, too bright in heat. They'd know someone built something. Whether that's good or bad depends on who's watching and whether they care. There's also the question of maintenance. A Dyson Swarm doesn't maintain itself. It's made of machines, and machines break. Over centuries, over millennia, things degrade. Collectors fail. Orbits drift. Systems need repair or replacement. You're not building a monument. You're building a garden, something that needs constant care, constant attention. If you stop tending it, it falls apart. And if it falls apart, you lose the energy. You lose the infrastructure. You lose everything you built. So you can't stop, ever. You're committed now. For as long as your civilization exists, you're maintaining the swarm. Is it worth it? That's not a question with an easy answer. It depends on what you value. If you want to survive, to grow, to reach for something beyond the limits of a single planet, then yes, it's worth it. But if you're content with what you have, if you don't want to spend centuries or millennia on a project that won't pay off for generations, then maybe it's not. Maybe you stay where you are. Maybe you don't build the swarm, and that's fine too. There's no moral imperative here. No cosmic law that says you have to keep growing. Some civilizations might choose to stay small, to live within their means, to never reach for the stars. But if you do reach, if you take that first step and keep going, the destination is extraordinary. It's not utopia, it's not paradise, but it's something. A future where energy isn't the bottleneck anymore, where you're limited only by imagination and time, where the sun, that distant burning sphere we've stared at since the beginning, becomes something we can touch, something we can use, not worship, not fear, just use. We're not there yet. We're not even close. The gap between here and there is so vast it's hard to see across. Centuries, probably. Millennia, maybe. And that assumes we don't destroy ourselves first. Assumes we solve our problems down here before we start solving them up there. Climate change, political instability, resource depletion. All of it has to be managed, or at least survived. Before we can think seriously about building a swarm, we have to make it through the next few centuries before we can worry about the next few millennia. But it's possible. That's the thing. It's actually possible. Not easy, not soon, but possible. And that's worth remembering, because for most of history, humanity has been trapped. Trapped by gravity, by distance, by energy. We've built what we could with the tools we had, but there was always a ceiling, always a limit. The Dyson Swarm is the first step past that ceiling, the first real attempt to break free. And if we ever manage it, if we ever see that cloud of collectors orbiting the sun, drinking in light, feeding energy back to the worlds we've built, we'll know we made it. We'll know we're not trapped anymore. The sun will keep burning for billions of years, and if we do this right, we'll be there to see it. All of it. Not just the beginning, not just the end, everything in between. That's the promise of a Dyson Sphere. Not power for its own sake, but time. Time to grow, time to learn, time to become something more than we are now. And maybe, in the quiet of some distant orbit, thousands of years from now, someone will look back at this moment, at us, at the strange, fragile species that burned fossil fuels and argued over borders and couldn't imagine a future beyond its own planet. And they'll wonder what we were thinking, or maybe they'll just be grateful we took the first step.